And welcome to another episode of Standing on the Shoulders of Giants. This week we will be looking at Albert Einstein and his theories of special relativity and general relativity. So thinking heads on. There is no more famous name in the field of physics than Albert Einstein. His origin story has become the stuff of legend. A brilliant young scientist toiling away in a patent office, who then revolutionized the world of science with that famous equation E equals mc squared. But what exactly did Einstein do that was so revolutionary? How did he develop his famous theory of relativity, and how did it change our understanding of how space, time, light and gravity work? Finally, how did Einstein's colleagues and today's scientists test such seemingly theoretical and intangible concepts? Albert Einstein was born in Germany in 1879 and spent much of his childhood in Munich, where his father and uncle ran a company that manufactured electrical equipment. From an early age, Einstein had a particular enthusiasm for maths, working his way through algebra and geometry books on his own. By his early teens he had moved on through calculus and developed a strong interest in physics. To Einstein, mathematics was the perfect language for describing and understanding nature. Einstein is sometimes imagined as a bit one-sided, a reputation that might come from his reportedly failing an entrance exam for the Swiss Federal Polytechnic School in Zurich. It also fits with an often deployed stereotype that mathematical geniuses may be strong in one area but deficient in others. To the contrary, Einstein had developed early interests in philosophy and music. He was a classically trained violinist and kept up his playing throughout his entire life, describing himself as thinking and daydreaming in terms of music. Like physics, music has deep mathematical roots. Einstein's passion for maths and physics did not, unfortunately, translate into a teaching position after he had finished his studies. At least not right away. In need of a job, Einstein began working at a patent office in Bern, where he continued studying science and philosophy and doing theoretical physics research for his PhD. Much of his patent work was focused on new technologies with electricity and clocks, combined with the work that his father and uncle did making electrical equipment. This likely sparked one of Einstein's first groundbreaking discoveries, special relativity. Einstein's special theory of relativity grew out of some apparent contradictions between two of the fundamental pillars of physics: Newtonian mechanics and electromagnetism. These two topics are taught side by side at universities around the world, and usually make up the first year of a physics student's college education, but taken together they don't quite seem to get along. To understand why, let's look at a basic principle of special relativity. The first is that the speed of light is always the same. Imagine a baseball player standing on the pitcher's mound and throwing a 90-mile-an-hour fastball to the home plate. You know exactly how fast the ball was moving, 90 miles an hour. Now let's put the same pitcher on the back of a train moving 40 miles an hour. If he throws his fastball straight off the back of the train, the ball is really only moving 50 miles an hour. Newtonian mechanics tell us that you have to subtract the speed of the train to measure the ball's true velocity. Now let's give our pitcher a flashlight. If he shines a flashlight from the pitcher's mound to the home plate, the light is moving at the speed of light, about 186,000 miles per second. What about when the pitcher is standing on the moving train? According to Newtonian mechanics, we might imagine the light as little individual particles and picture those particles slowing down by 40 miles an hour. But according to the laws of electromagnetism, that light is acting like a wave with a constant unchangeable speed, the speed of light. The light of that wave might be stretched by the speed of the train. This is the phenomenon we talked about in an earlier program known as redshift, but the speed of the wave is unchanged. Both answers can't be right, and they're not. Light will leave the train riding pitcher's flashlight at 186,000 miles per second, regardless of how fast the train is moving. But why? Newtonian mechanics did just fine at predicting the behaviour of the baseball, so why did it get light so wrong? Other research in the late 19th century had tested and proven the theories of electromagnetism, showing light acting like a wave. But what made light special? Why couldn't Newtonian mechanics and electromagnetism settle on a definitive answer? Einstein devised his special theory of relativity to reconcile these two seemingly at odds theories. He declared that the speed of light must be constant and that relativity must be a fundamental tenet of physics. Relativity, simply stated, says that the laws of physics must stay the same everywhere. Everywhere here refers to what we call different frames of reference. In our pitcher on a train scenario, the laws of physics must be the same for the pitcher riding the train and for someone waving from the side of the tracks as the train goes by. The two positions represent two different frames of reference, altered by their relative positions and speeds, but still beholden to the same laws of physics. These two statements, the speed of light is constant and the laws of physics must stay the same everywhere, and testing them mathematically, became the cornerstone of Einstein's work. His famous equation is one example of these mathematical consequences, describing the energy of an object as equal to its mass times the speed of light squared. Before Einstein, classical mechanics described objects as having either a kinetic energy, an energy it has because it's moving through a system, or a potential energy, the energy stored in an object because of its position in a system. E equals mc squared described a more fundamental energy, known as the rest energy, and boils down the relationship between something's energy and its mass to this simple equation, connecting them by that constant, the speed of light. The equation works across any frame of reference, satisfying Einstein's key rules. Another strange implication comes when we consider time. If we give clocks to both the pitcher and our train watcher, perfectly tracking how they experience time, they'll each see their own clock as working normally. But if they check each other's clocks, things get strange. The clock on the train will run ever so slightly slower, reflecting that in the train's frame of reference time has actually slowed down. At the speed of a train, this effect is infinitesimal, but in frames of reference moving at much faster speeds, say approaching the speed of light, time will slow down dramatically. This phenomenon is known as time dilation, and while it may seem strange, it's a crucial detail of special relativity that keeps time and physics working perfectly, even for a person in a very fast-moving frame of reference. Einstein published his work on special relativity and 3 other groundbreaking research papers in 1905 at the age of 26. Contrary to his legend, his theory didn't quite erupt from nowhere out of an obscure patent office. Einstein had been researching and publishing for years and acknowledged the work of fellow physicists like Max Planck and Hermann Minkowski as important influences. Still, the theory was seen as a great and triumphant scientific leap. His fellow physicists, many of whom had been grappling with the puzzling contradictions of mechanics and electromagnetism, were quick to accept his theories. His solution was simple, elegant, and worked perfectly. Almost. Einstein's new theory and his new explanations of how space and time worked across different frames of reference still made one important assumption. Remember, relativity states that the laws of physics must stay the same everywhere, but today we call Einstein's work from 1905 special relativity. In special relativity, Einstein kept this idea simple. He imagined the laws of physics hard at work in any inertial frame of reference, in other words, in any place that didn't have a net force acting on it. Remember our picture standing on the train? Let's give him a break. Imagine him walking back through the train, sitting down and pouring himself a glass of water. Even though the train is moving 40 miles an hour, from our picture's perspective, everything inside the train is sitting still and pretty much normal. He can walk to his seat, sit comfortably in his chair, and the water he pours drops straight into his glass, just like the laws of physics say it should. The train is moving slowly, and he is in an initial frame of reference. So far, so good. But what happens if the train suddenly speeds up to 80 miles an hour? Suddenly the pitcher stumbles on his way to his seat, or he gets thrown back into his chair, or the water he is pouring into the glass winds up all over the place. This happens because the pitcher's frame of reference isn't inertial anymore. The train accelerated, and he felt that as a sudden change in the forces acting on him. The laws of physics haven't changed, but we have introduced a new effect, the acceleration of the train. For Einstein's theory of relativity, going from special relativity to general relativity, that is, making the laws of physics the same in all frames of reference and not just inertial frames of reference, meant contending with a crucial and ambiguous source of acceleration. It's an acceleration we're all experiencing right now, holding our feet on the floor and keeping all the things around us from floating away. It's acceleration due to gravity. Scientists have known the math of gravitational attraction since Isaac Newton, and while Einstein's special theory of relativity did a great job on reconciling mechanics and electromagnetism, he knew it didn't quite work for gravity. Special relativity had explained the relationship between space and time. General relativity, which Einstein developed between 1907 and 1915, expanded his work to describe the relationship between space, time and gravity. We imagine this today by invoking the concept of space-time, with space and time inextricably linked to make up the fabric of our universe. In special relativity, we imagine space-time as flat, with something like light travelling neatly along straight lines. But in general relativity, when we introduce gravity, space-time becomes curved. An object with a loss of mass, like a planet or a star, will affect space-time thanks to the effects of its gravitational field, warping the fabric of the universe and appearing to bend the path that light takes as it travels, changing its apparent position and travel time. Tying together gravity, space and time is today considered one of Einstein's greatest discoveries, and he made many. Oddly enough, his Nobel Prize in 1921 actually had nothing to do with relativity. Instead, it mentions another discovery he made in 1905, the photoelectric effect. This is the emission of electrons caused when light hits a surface. The same effect that we talked about in an earlier program when Kent Ford was designing the image tube in the 1960s that he and Vera Rubin used to discover dark matter. Even so, today we're still testing and exploring the implications of general relativity. So far, this might not seem to have all that much to do with our astronomy. We've been talking about pictures, glasses of water and speeding trains. Still, on a cosmic scale, the interaction between space, time, gravity and light, the primary tool astronomers have at our disposal for studying the universe, is a cornerstone of how we explain the way the universe works. Einstein's general theory of relativity began to coalesce in the mid-1910s, and he published his primary results in 1915. Around that time he also became a member of the Prussian Academy of Sciences and moved to a prestigious directorship and research position in Berlin. It marked a new step in a difficult relationship between Einstein, his science, and Germany. In the early days of World War I, Einstein's theory of relativity was seen politically as a triumph of German science over the laws of motion and gravity made famous by Englishman Isaac Newton. In Britain, Einstein's work was framed as politically unpalatable, and engaging with it was met with wary skepticism. At the same time, Einstein was eager to find a champion and collaborator who could put his theory to the test. He had already conceived of one elegant and straightforward means of proving something as seemingly cerebral as the bending of space-time by mass, and the test involved astronomy. According to general relativity, our own sun should influence the light of background stars as it passes in front of them. The subtle warping of space-time from our sun's mass should deflect the path of the light as it travels from the background stars to Earth, subtly shifting the apparent position of stars near the sun. Einstein's general relativity equations allowed him to calculate exactly what this expected shift would be, and while it was small, the observational astronomy experts of the era, like George Ellery Hale, confirmed to Einstein that it would be detectable with cutting-edge telescope technology. The difficulty, of course, is that when the sun is visible, it outshines the light of any stars in the sky. For the best test, astronomers would need to observe stars incredibly close to the sun, right at the most blinding point in the daytime sky. The only way to accomplish this would be during a total eclipse. At the moment of totality, a few short minutes when the moon perfectly blocks the sun would be in a position to bend the light of background stars, and the stars themselves would actually be visible. Astronomical photographs of those stars near the sun taken during an eclipse would then show whether there was a shift in apparent position predicted by Einstein. The challenge became testing this theory during an actual eclipse. Einstein was not an observational astronomer himself and needed collaborators who were astronomical experts to test his theory. Eclipses are also rare and difficult to observe. They happen less than once a year on average, and can only be seen from a narrow swathe of the Earth's surface that happens to lie beneath the path of the moon's shadow. An expedition to Brazil for 1912 eclipse was foiled by weather. A second attempt in August 1914 took some of Einstein's German colleagues to Crimea, just weeks after Germany declared war on Russia, and political strife cut the expedition short. General relativity may have offered a grand solution to physicists' models of space, time and gravity, but even groundbreaking science seemed to be bending under the influence of global politics. This was when Arthur Eddington entered the story. Eddington was a British astronomer, 3 years younger than Einstein, born and raised in northern England in the Quaker faith. By the mid-1910s he was an expert observational and theoretical astronomer, studying everything from asteroids to detailed theories that could explain the strange Cepheid variable stars discovered by Henrietta Leavitt at Harvard. His research ultimately led to groundbreaking discoveries on the interior physics of stars, including discovering that stars are powered by internal fusion, and describing the physical limits on how luminous stars could get. Eddington held the prestigious position as Secretary of the Royal Astronomical Society during World War I. His Quaker pacifism meant that, when letters describing Einstein's theory of relativity arrived on his desk, he was perfectly willing to strike up a correspondence with a German scientist, and his scientific prowess made him uniquely suited to test the implications of general relativity. Encouraging his British colleague to pursue confirmation of a German theory in the midst of World War I was no easy feat, But Eddington ultimately worked with colleagues at the Royal Astronomical Society to organise 2 expeditions to the Atlantic equator in 1919, sailing with huge telescopes and heaps of equipment to set up portable observations beneath the path of the eclipse in Sobral, Brazil, and Principe Island off the coast of West Africa. The 2 stations were meant to offer redundancy. The astronomers would have only minutes to capture the photographs that would prove Einstein right or wrong, and a poorly timed cloud or rainstorm at an inopportune moment could ruin years of planning and months of expedition travel. The weather cleared at both stations, and Eddington and his colleagues captured crucial observations of the stars near the Sun during the eclipse. Eddington's early analysis was enough to confirm that yes, the star's apparent position had moved. Einstein had been shown to be correct. When the final analysis of the data was released, it was heralded as a major worldwide news story. Eddington's discovery made the front page of newspapers all over the world and catapulted Einstein and his newly proven general theory of relativity to worldwide fame. At first, physicists and astronomers were a bit more cautious than the general public in embracing Einstein's work. General relativity was a thorny and difficult theory to understand mathematically, and it was put to the test again and again for decades afterwards. Many more eclipse observations ultimately backed up what Eddington and his colleagues had found, cementing in place this first confirmation of Einstein's model for space, time, and gravity. Today, general relativity has become a core tenet of physics with effects that we can see all around us once we know what we're looking for. Some applications of general relativity are surprisingly practical. The GPS navigation you use in your car or on your smartphone only works thanks to Einstein's special and general relativity. Keeping track of time down to a fraction of a second and pinpointing a location on our planet with an accuracy of just a few feet is an incredibly complicated task. To do it correctly, GPS technology has to account for the relative motion of the satellites, the Earth, and even your car, tweak the clock it uses to match times across different frames of reference, and even accommodate changes in the curvature of space-time caused by gravitational effects that vary as you move away from Earth's surface. Other general relativity effects are still best observed with powerful telescopes. The bending of light predicted by Einstein and seen by Eddington can also take a more extreme form if we look further out into the cosmos. Another prediction of general relativity notes that a very massive object can warp space-time sufficiently, so much as that it begins to act like a lens that substantially distorts and magnifies the background light. Other physicists recognized this possibility in general relativity equations, and Einstein himself published a paper on it in 1936, but it was astronomer Fritz Zwicky who first proposed that this effect should be particularly obvious by using massive clusters of galaxies. When it comes to finding lots of mass concentrated in one place, galaxies are a perfect candidate. Our own Milky Way has an estimated mass of 1.5 trillion suns, including stars, gas, dust and dark matter, and in galactic terms we're pretty average. Zwicky realized that using a massive galaxy as a space-time warping lens would produce immensely strange and distorted images of other, more distant galaxies whose lights pass close to the lens. The maths of gravitational lenses predicted some spectacular sights, training a kind of gravitational funhouse mirror on far-away galaxies. Background galaxies distorted by a massive lens would look brighter than expected, and would be bent into curved slivers and offset from where they would appear in the night sky without the effects of general relativity. The whole problem comes down to geometry, and a sufficiently perfect alignment of a lens and a background object would produce multiple images or even a perfectly bent ring arcing around the lens. In 1979, a team of astronomers in Arizona discovered what looked like two quasars, brilliantly luminous cores of distant galaxies with supermassive black holes at their centers. When they looked closer, however, they realized that the two quasars were unusually close in the sky and looked suspiciously similar. More observations ultimately revealed that these two quasars were in fact a single background quasar, multiply imaged and distorted by an enormous galaxy lying between the quasar and us. The match between the two quasar images wasn't perfect. The light from the two lensed images travelled along slightly different paths and arrived at Earth at slightly different times, with uniquely distorted appearances. But it was close enough to prove that the quasars were being lensed, and that the lensing was indeed happening according to Einstein's general theory of relativity. Today we see incredible and dramatic examples of gravitational lenses in observations of distant galaxies and galaxy clusters. You may remember images from the Hubble Space Telescope showing a host of distorted and curved background galaxies bent by massive objects sitting between us and them. Astronomers have observed perfect rings, weirdly shaped galaxies malformed by the effects of multiple lenses, and even a supernova that appeared in our sky 4 times thanks to being multiply lensed by a huge galaxy. Enormous galaxy-sized gravitational lenses and the images they produce may be dramatic, but remember, even low-mass objects can warp space-time and lens light. Eddington's eclipse experiment measured the shift of background stars thanks to the mass of the Sun. Today astronomers carefully monitor the brightness and lensing effects of thousands of distant potential suns. General relativity predicts lensing effects so exactly that any deviation from the expected behavior could indicate there's a bit of mass where we don't expect, and for a small star like our Sun, that extra mass sometimes comes from an orbiting planet. The implications of Einstein's general theory of relativity are numerous and immensely far-reaching. From Eddington's 1919 eclipse expedition to the spectacular gravitational lenses and accurate GPS trackers we see today, evidence of Einstein's incredible and successful theory is all around us. Now, Einstein's work wasn't infallible, and there are some details of general relativity that we're still exploring and testing today. Dark energy is one example. Einstein's theory of general relativity originally predicted that the universe must either expand or contract. Einstein recognized this in his equations, but saw it as an error rather than a potent prediction. After all, at the beginning of the 20th century, astronomers seemed to clearly see a static and unchanging universe, and the idea of expansion seemed absurd. Einstein's fix was to simply tack a number onto his equations, known as the cosmological constant, to allay these concerns. After work by Edwin Hubble and others revealed an expanding universe, he took the number back out, but it's been reinstated today. What Einstein called the cosmological constant is what astronomers today know as dark energy, the mysterious energy that helps to drive the expansion of the universe. Still, even with tweaks to accommodate the shape of our universe, Einstein's general theory of relativity has proved to be an exceptional guide for how space, time and gravity work, and we're still finding new evidence of just how well this theory describes physics. One of the most literally earth-shaking implications of Einstein's theory, a discovery that Einstein himself imagined would be impossible to detect, will be the topic of our next program: gravitational waves. Okay, well, the water clock has finally filled the jug, and if I hang around much longer I'm going to get very wet feet. Before I go, just a quick conundrum for you to think about. If a catcher standing on the last carriage of the train caught the ball being thrown by the pitcher towards him, would he actually feel the ball hit his hand at 50 miles an hour or 90 miles an hour? Remember, the train is travelling at 40 miles an hour. That's something to think about over the week. Please remember, stay safe, look after one another, and I'll see you again next week. Bye for now.